Click the bell icon to get latest videos from Ekeeda.
Hello friends, in today's session we are going to study the factors influencing hardness of water. Now whenever you talk about hard water, what exactly is hard water? Hard water is any water which has some sort of dissolved impurity in it which we cannot remove easily. Now these dissolved impurities can happen due to various reasons. There can be dissolved minerals, dissolved salts, especially at times there are dissolved gases. Now these gases apart from oxygen which are dissolved in water, and because of that it leads to hardness of water. Today we will see all the different factors which lead to hardness of water. Factors influencing hardness of water or causes of hardness. There are mainly three causes of hardness. The first is dissolved minerals. When we talk about minerals, we talk about all kinds of salts, we talk about all kinds of ions and all kinds of other impurities as well. The second is dissolved oxygen. Now we all know that water itself consists oxygen. That means the molecule of water is H2O, that is 2 hydrogens and 1 oxygen. Apart from that, if there is extra oxygen added to the water, that extra oxygen will also lead to impurity of water, and that impurity definitely leads to hardness. Any kind of dissolved impurity leads to hardness. And apart from H2O, that is the oxygen, the proportion or the percentage of the oxygen which is present in the molecule of the water, apart from that, if we have extra oxygen in the water, that is not desirable. The third is dissolved carbon dioxide. Again, carbon dioxide is a basic gas CO2 which is dissolved in water in many cases. Because of many influences or many types of effluents which are thrown into water, because of that CO2 gets scattered. Even we have organic compounds in water. Now these organic compounds react with the oxygen and produce CO2, and this CO2 may just remain dissolved in water. So because of all these basic factors, we have hardness in water. We should understand one thing, that all the three factors are dissolved. Anything which is not dissolved, any impurity which is not dissolved can be easily removed either by filtration process or any other physical methods or means. But if we have dissolved substance in it, we'll have to produce any kind of chemical reactions or any other kind of processes wherein these dissolved minerals or soluble minerals, oxygen or carbon dioxide, will get converted into something which is insoluble and then can be filtered out easily. We'll see in detail each and every one of them and how they affect the hardness of water. Starting with dissolved minerals. Dissolved minerals are of heavy metals. So for example, let us take water which is from streams or rivers. Now this water comes from the mountain tops. So when water is flowing as a stream from the mountain tops, it is cutting through the rocks. It's cutting many rocks, and all of these rocks have some kinds of salts or minerals. Each and every rock is made up of some kind of mineral. When the water is continuously cutting through the rocks to make its way down, it is actually dissolving many minerals which are there in the rocks into itself. And these minerals into the water lead to the hardness of water. So dissolved minerals can be heavy metals. They get assimilated in water in the form of their soluble salts. Assimilation means getting dissolved into a water, being a part of the water. That means all these salts which are soluble. For example, if I take an iron block, which is pure iron block, and I place it in water, that iron block will never get mixed in water. But if I take an oxide of iron or chloride of iron, any kind of salt of iron, that salt will get dissolved in water. And thus these minerals get dissolved in water because of the soluble salts. Thus contact with mineral influences hardness. Only with the help of contact, we do not need any other kind of energy. We do not need to provide any kind of heat, energy or anything to it. Only contact of water with such kind of salts makes the salts dissolve in water. Dissolution is followed by hydration process, in which minerals like CaSO4 anhydrite or MgSiO4 olivine react with water. That means that after it gets dissolved, the next process which happens in water is hydration process. What exactly is hydration process? Hydration means addition of water. To anything, if you add water to it, that thing gets hydrated. So over here we are taking CaSO4, which is an anhydrite, or MgSiO4, which is an olivine, and we are making hydration process to it. We need to remember that there are two processes. The first process is the dissolution of the process. That means when water comes in contact with CaSO4, CaSO4 will get dissolved in water. That is the first process. The second process is the hydration process. That means once CaSO4 is dissolved in water, the next process CaSO4 will incorporate few molecules of H2O into itself. And once it operates few molecules into itself, it becomes an anhydride over here, which is known as gypsum. Let us see the chemical reaction. We have CaSO4, which is anhydrous, plus 2H2O. Now this 2H2O is the water in which it has got dissolved. The process is known as hydration because there is addition of water into CaSO4. This forms CaSO4.2H2O. This is known as gypsum. Volume increases by approximate 33%. So what is happening over here is this anhydrous CaSO4. Whenever we talk about something which is anhydrous, that means CaSO4 itself is powderish in form. But once you add water to it, it will take in water. It will take two molecules of water. One molecule of CaSO4 will take two molecules of water and it will form gypsum. Over here, if you will notice, I have put a dot. That means there is no bonding between CaSO4 and H2O. H2O itself is a molecule. CaSO4 itself is a molecule, but both of these molecules are just attached. There is no kind of ionic or covalent bond over here. There is only attachment. That means they are together, but they are not bonded. Such water molecules which are just attached to other molecules are known as WOC, water of crystallization. That means these water molecules give crystallization to the CaSO4. The CaSO4 on the reactant side was just powder in format. On addition of two molecules of water will become a crystal. When you take this gypsum, gypsum is actually a crystal form. If you heat it in a pan, all the water will get evaporated. Why? Because water is just loosely attached to it. It is not bonded. The first thing that will happen to CaSO4 to H2O under any reaction is that the water will just evaporate out. Once the water evaporates out, this crystalline gypsum will again get converted into the anhydrous CaSO4, that is powder. So you have CaSO4, you add water to it, it becomes a gypsum, which is a crystal. You remove water out of it, it again becomes the powder, that is the anhydrous form of it. Whenever you add water to an anhydrous compound, it will give crystallization to it. That means that powder will start looking like a crystal now. It also adds up to the physical qualities of it, and at times it also changes the color of the powder. Because of addition of two molecules of H2O into CaSO4, the volume is increased by 33% because water is giving shape to it. Now whenever we see this, let's see the balancing of it. I have one CaSO4 on the reactant side, one CaSO4 on the product side, two water molecules on the reactant side, two water molecules on the product side. The only difference between the reactant side and the product side is the reactant side has a plus sign, but on the product side it's a dot. That means it is water of crystallization. The next thing what do we have over here is Mg2SiO4. This is nothing but olivine. Now to this olivine I have taken XH2O. For CaSO4 we knew that it needs 2H2O. But for olivine we do not know the amount of hydrogen needed. It depends on the type of olivine and on the amount of olivine. And that is the reason why I have written over here XH2O. On the process of hydration it will form Mg2SiO4 dot XH2O, and this is known as serpentine. From olivine it forms serpentine with the help of XH2O. So over here I have Mg2SiO4 plus XH2O. The only difference on the reactant side and the product side is over here I have a plus sign. Instead of plus sign now I will have a dot. So Mg2SiO4 dot XH2O. Now this is nothing but my water of crystallization, and because of the water of crystallization my olivine will get a crystallized form in the form of serpentine over here. The number of Mg's on my reactant side is 2. The number of Mg's on the product side is also 2. The number of Si on the reactant side is 1. The number of Si on the product side is also 1. The number of oxygen over here is 4. The number of oxygen over here is also 4. When we talk about XH2O, we have XH2O on the reactant side, XH2O on the product side. So this is how the minerals get dissolved in water. The first thing that they do is dissolution. That means they get dissolved in water. The second thing that they do is hydration. After dissolving in water, they make sure that they take a certain amount of water molecules in them and form crystallized forms of themselves. The next thing we are going to learn is dissolved oxygen over here. Dissolved oxygen is also one of the major factors to influence the hardness of water. Now, dissolved oxygen may appear as D dot O dot. Now, this DO is a sign of writing dissolved oxygen. Dissolved oxygen influences oxidation and hydration of metal oxides, sulfides. What is happening over here? The first thing which is happening is oxidation. Oxidation is a process of addition of oxygen. That means if I have a metal or any component or any element, and if I add oxygen to it, that means the oxidation process is done and that entire metal is oxidized. Gaining of oxygen is known as oxidation. So the first process that happens over here is oxidation, and the next process that happens is hydration. Now if I have an oxidized compound, that oxidized compound can go and attack water molecules and get the process of hydration. Over here also there are two processes. The first is oxidation and the second is hydration of metal oxides, sulfides. And let us see the reaction over here. The first we have is magnetite. Magnetite is Fe3O4. On the arrow we have half O2 forming 3 Fe2O3. Over here if you see we have Fe3O4 and this entire Fe3O4 is twice plus half of oxygen. Oxygen over here is written as O2 and this O2 is half, so this 2 and this half gets cancelled and what remains is 1 oxygen. That means this oxygen is going to be added to my magnetite, which is Fe3O4, and this process is known as oxidation process. After addition of oxygen or after the oxidation process, what remains over here is hematite, that is 3 Fe2O3. Now let us first see only this part of the reaction and let us see the balancing of the reaction. Over here we have 2 Fe3O4 on my reactant side. Let us only take ferrous right now. So for my ferrous or my iron over here, this is 3 into 2, that is 6 over here. 6 ions on my reactant side. On my product side, if I see, I have 3 Fe into 2. So over here I had 3 down and 2 up. Over here I have 3 up and 2 down. But that does not make a difference because overall on my reactant side over here I have 6 Fe's. On my product side over here I have 6 Fe's. When we talk about oxygen over here on my reactant side, this is 4 into 2, 8 plus 1, 9 over here. 4 into 2, 8. Why? Because we have oxygen which is 4 and this entire O4 is twice. So 4 into 2, 8 plus I'm adding 1 more over here to this 8. So the number of oxygens on my reactant side become 9. Number of oxygen on my product side will be 3 into 3, that is again 9. Now this Fe2O3 I am doing a hydration process. Why? Because first we had the oxidation process and the next process which we had was hydration process. So now to this Fe2O3, which is also known as hematite, I am doing the hydration process over here, and because of the hydration process I am adding 2 water molecules. On the product side what I get over here is limonite. So when I am talking about this, now this will be my next half of the reaction, wherein I am taking 3 Fe2O3 in presence of hydration, that is 2 water molecules will form 3 Fe2O3 dot 2 H2O, which is known as limonite. Now let us see the balancing of this end of the reaction, that is 3 Fe2O3. So 3 into 2, that is 6 over here. Iron is also 6 over here. We have O3 on this side, O3 on this side. To this I am adding 2 waters, that is plus 2 H2O, which is dot 2 H2O, and whenever I write dot, this water is nothing but WOC, water of crystallization. This water of crystallization helps in making this into a crystalline format. So this is my entire reaction starting from magnetite. The first reaction which happens, the first process which takes place is oxidation process, wherein I am adding 1 oxygen to it, converting this magnetite into hematite. The next process which takes place is the hydration process, wherein I am adding water to it, and after adding water to it, what it forms is limonite over here, that is 3Fe2O3.2H2O. So in this entire process, the first thing is magnetite, the second is hematite, and finally limonite. So over here we have the sulfide of iron 2FeS2 plus 7O2 plus 2H2O. Now this is my reactant side, and two processes are happening over here. The first process is the oxidation process and the second process is the hydration process. So oxidation process and hydration process, both those processes are written simultaneously, and after oxidation and hydration happens, the products that we have are 2FeSO4 plus 2H2SO4. Now let us see the balancing of this reaction over here. We have two Fe's on my reactant side. On my entire reactant side, I have two Fe's. On my product side, on the entire product side also, I have two Fe's. Now I have S2, which is twice over here. That means 2 and 2, that is 4. I have 4 sulfurs on my entire reactant side. I have 2 plus 2, that is 4 sulfurs on my product side. We have S over here, which is twice. We have S over here also, which is twice. That means 2 plus 2, that is 4 sulfurs on the product side. So my entire Fe is balanced, my entire S2, that is 2S2, is also balanced. Plus we have 7O2. But over here we should not consider only this, because over here also we have O. Whenever we are trying to balance a reaction, we balance the reaction of the entire reactant side with the entire product side. So over here we have 7O2 over here, and this is 2H2O. That means 7O2, that means 7 into 2, which is 14, plus 2H2O, that means 2, 14 plus 2. So number of oxygens totally on my reactant side will be 16. The number of oxygens on my product side are 4 into 2, 8, and 4 into 2, 8. 8 plus 8 is also 16. That means this O4, this entire O4 is twice. That means 4 into 2, that is 8. Over here also I have O4, and this entire O4 is twice. Again this will be 4 into 2, 8. So overall totally I have 8 oxygens over here. Overall totally also I have 8 oxygens over here. So number of oxygens are also balanced on my reactant side and the product side. Finally we have 2H2O, out of which the oxygen is balanced. The only thing which is remaining to get balanced is my hydrogen. That is, I have 4 hydrogens on my reactant side, because it is 2 into 2, which is 4. And over here also I have 2H2, that is 2 into 2, that is 4 hydrogens on the product side. Thus this is my entire balanced reaction over here. That is the Marasite, that is FeS2, 2FeS2 plus 7O2 plus 2H2O. That is, two processes are happening: oxidation because addition of oxygen is there, and hydration because addition of water molecules are there, forming 2FeSO4 plus 2H2SO4. The next we have is dissolved carbon dioxide. The pH of water decreases due to dissolution of carbon dioxide. Now we have a pH scale from 0 to 14, and 7 is the neutral. So when from 0 to 14, 7 is the neutral, which side over here is known as acidic. From 0 to 7 is acidic, and the side over here is known as basic. That means that if the pH increases, the water is going to the basicity level. If the pH decreases, the water is going to the acidity level. Water itself, pure water, is neutral. That means it will be at pH 7. When we add impurities to it, the impurities either increase the pH or they decrease the pH. If they are increasing the pH, they are making pure water basic. If they are decreasing the pH, they are making pure water acidic. Now when we are specifically talking about CO2 over here, the pH of the water decreases. And since the pH decreases, that means it is going down from 7. That means the acidity of the water increases. Due to this, the dissolution of other minerals also increases. Now there are many minerals which will not get dissolved in pure water, but these minerals can get easily dissolved in acids. Now since my water is turning into an acid, because from 7 it is going downwards into an acidic form, there are many minerals which can get dissolved in acidic water. That means carbon dioxide itself first gets dissolved in water, converting that soft water into hard water, and second thing, aids all the other minerals also to get dissolved in water because it is eventually decreasing the pH of the water. That means converting that water into an acidic form of it will help all the other minerals to get mixed in it and dissolved in it better. That is the reason why CO2 harms water in various ways. It itself will give hardness, and it will also aid other reagents and other minerals to get dissolved in it, and therefore leading to more hardness of water. The following reactions are self-explanatory that how dissolved CO2 influences hardness of water. We'll see certain reactions and see the effect of CO2 on water. Now imagine a water stream which is passing through rocks. Now these rocks have CaCO3 in them. If this CaCO3 gets mixed in water, that is pure water, that CaCO3 will not affect water at all because those are insoluble in water. CaCO3 always precipitates out of water. So if I have water and I add CaCO3 in it, that water will not get converted into hard water because CaCO3 will not get dissolved at all. But now, if the water contains CO2, a little amount of CO2 as well will pass through the rocks, and now the CaCO3 will get inside water, then that CaCO3 will start reacting with CO2 which was already present in water. And because of this reaction of CaCO3 and CO2, they form something which is soluble in water. Now this soluble impurity will increase the hardness of the water, or it will contribute to the hardness of water. That means the innocent CaCO3 which wasn't helping in the hardness of the water at all will now start contributing to the hardness of the water because of the CO2 which is present in the water. So CO2 itself leads to hardness of water, plus it helps other insoluble minerals present in the water to get dissolved in them and lead to further hardness of water. Let us see the reactions of the same. So over here I have insoluble CaCO3 which is coming from the rock. Now I have CO2 and H2O. I have not shown an upward arrow to the CO2 because this CO2 is dissolved in water. Now this is my CO2 present in water containing CO2. This is my entire solution. To this solution I am adding CaCO3. Now this insoluble CaCO3 forms CaHCO3 twice, which is now soluble in water. One molecule of CaCO3 plus one molecule of CO2 plus one molecule of water makes the insoluble impurity into a soluble impurity, and this soluble impurity leads to hardness of water. So here I have CaCO3, I have one calcium on the reactant side, one calcium on the product side. Let us count the number of carbons over here. I have 2 carbons on the reactant side. Over here also this HCO3 entire thing is twice, therefore this I have 2 carbons on the product side. The number of oxygens over here are 3 plus 2 5 plus 1 6. Over here the number of oxygens are also 3 into 2 6, and the number of hydrogens are 2. Over here also the number of hydrogens are 2. That means this is an overall balanced reaction. If you notice, there is nothing on the arrow as well. Why? Because this reaction does not need any external influence. It's a spontaneous reaction. Whenever CaCO3 will see CO2 in presence of water, it will immediately form soluble CaHCO3 twice. This is calcium carbonate forming calcium bicarbonate, which will lead to temporary hardness of water. The next over here we have is MgCO3 plus CO2 and water. This is CO2 and my water solution. This MgCO3 is again insoluble and it is from the rocks. Again, it does not need anything on the arrow. It needs no energy, no external interference, nothing. It will immediately form MgHCO3 twice, which is magnesium bicarbonate, and this magnesium bicarbonate is soluble in water. If you see the balancing of this reaction, I have 1 Mg on the reactant side, 1 Mg on the product side. I have 1 and 2 carbons on the reactant side. I have 2 carbons on the product side because this entire HCO3 is twice. Then I have the number of oxygen, which is 3 plus 2 5 plus 1 6 oxygens on my reactant side. This is also 3 into 2 6, that is 6 oxygens on the product side. Finally, counting the number of hydrogens over here, I have 2 hydrogens on the reactant side and 2 hydrogens on the product side. Again, the insoluble impurities from the rocks get soluble when they are mixed with CO2 in presence of water, forming a soluble impurity. This is magnesium bicarbonate, and magnesium bicarbonate leads to temporary hardness. Both of these are bicarbonates of calcium and magnesium, and both of these will lead to temporary hardness, and temporary hardness of water can be removed by boiling of it. The third point is CO2 also influences conversions of Ca, Na, K, Fe, that is calcium, sodium, potassium, and iron silicates and aluminum silicates, not only the carbonates or the bicarbonates. So other than that, CO2 also influences conversion of calcium, sodium, potassium, and ferrous silicates and aluminum silicates. So it also takes the silicates of various elements over here, and it also helps in the conversion of that from insoluble impurities to soluble impurities, which lead to hardness of water present in rocks into soluble carbonates and bicarbonates. Some of them get converted into free silica. Let us take an example over here. We have K2O.Al2O3.6SiO2 plus CO2 plus H2O. Now whenever you see this whenever you see this complex over here, this complex is attached by dots. That means this K2O has bonding in it, Al2O3 also has bonding in it, this 6SiO2 also has bonding in it, but there is no bonding between them. There is only attachments between them. These dots represent the attachments. So over here we only have attachments between them, plus CO2 plus 2H2O forming Al2O3 dot 2SiO2 dot 2H2O plus K2CO3 plus 4SiO2. So what is happening over here? This Al2O3 is as it is. It has 2 SiO2s. Out of this 6 SiO2s, 2 SiO2s are gone. So now we are remaining with 4 SiO2s, and these 4 SiO2s are written over here. Then we have dot 2H2O. So this 2H2O is also gone over here. Now what is remaining over here is this CO2 and this K2O. Now this K2O and this CO2 combine together and form K2CO3. Now let us see the balancing of this reaction over here. We'll balance it in terms of molecules and in terms of elements, because over here it's a long reaction. We'll see the simplest way of balancing. The simplest way of balancing is first finding out what is exactly the same. Over here I have one entire Al2O3 on the reactant side. On the product side also I have one entire Al2O3. Now again I have 2 SiO2s. On the reactant side I have 6, but on the product side I have 2. That means I'll have to do 6 minus 2, and this will lead to 4. That means after giving 2 SiO2s over here, I should have 4 SiO2s remaining, and these 4 SiO2s are over here. So 4 plus 2, 6. So even this has got balanced. This has got balanced. Now let us focus on H2O. I have 2 H2Os on my reactant side, 2 H2Os on the product side. So even this has got balance. Now what is remaining over here is K2O and CO2. Now this K2O and CO2 combine together to form K2CO3. K2C and 2 plus 1, that is 3, O3, K2CO3. Now this is my entire reaction. These products, that is dissolved salts, fine clay and free silica, get collected in water, and because of that also it increases the hardness. So in this session we studied about all the factors influencing the hardness of water. There are 3 main factors: dissolved minerals, dissolved oxygen and dissolved carbon dioxide. We studied with the help of reaction how dissolved minerals affect the hardness of water, how dissolved oxygen affects the hardness of water, and for carbon dioxide it not only affects the hardness of water but also helps other minerals to get dissolved in water and affect the hardness of it. Thank you so much for watching this video. Stay tuned to Ekeeda and subscribe to Ekeeda.